So what we're going to go over today is probably going to seem pretty familiar to you. It's mostly going to be a review from Science 9. So that's going to be things like history and structure of the atom. So should be, like I say, pretty familiar to you. So we're going to look at some history stuff, why we thought the atom looked a certain way, and then kind of what came along to change our idea. It's kind of just an important progression so we understand how the scientific method works and things like that. And then, of course, we'll look at the parts of the atom. What are the three parts of the atom? Oh, I know somebody knows it.
Proton?
Proton is one.
Neutron?
Neutron. Electron. Okay, three parts of the atom. We're going to look at, obviously, how we know how many of each there are, where they are, why we believe that's where they are, that kind of thing. All right, so like most sciences, chemistry was something we used rather than something we truly understood. Okay? We used chemical and physical properties of materials for a long time without ever really understanding why they worked the way they worked. They just worked, so we used them. Okay, which is true for so many things in science. But what we'll look at today is kind of how we went from this practical use of chemistry to a more kind of deductive science. Okay. All right. If you're worried about like copying everything on this, don't. Okay, it's not a super important slide. If there's something that's important for you to copy, I'll let you know. Okay, plus you have the notes package that would have all of this in it. Okay, anything that goes up on the board here is going to be in the notes package, unless I say, hey, add this. Okay, then you should add. All right, so the idea of the atom actually has been around for a long time, but wasn't accepted until 200 and some years ago. But the Greeks, a Greek, actually came up with the idea a few thousand years ago. But it was kind of shouted down, okay? Because the Greeks believed that everything was made of 4 elements. Okay? And those 4 elements were earth, air, fire, and water, which made complete sense at the time. Okay? The reason it made complete sense is they sort of had a periodic table of sorts. They knew that, let's say, lava, something that the Greeks would have had experience with because, Greece is a volcanic island. They knew that lava was some parts earth, some parts fire, and some parts water. Okay? And here's why they thought that. It was hot, it came out of the ground, and it flowed like water. Okay? So it made sense for them to say lava is a mixture of these 3 things. Steam, similar. Steam would have been some parts fire, some parts water, and some parts air, because those are the 3 things you put together to make it. Agreed? Okay. So it made good sense at the time for them. Okay. And not everybody was, super educated or anything like that, so this was kind of a common sense approach that made good sense, and there was nothing around to say that that was wrong. Okay. And that's how science works. Until we have something that can prove an idea wrong, we accept that idea. Now, at that same time, a guy named Democritus, okay, came up with this idea that matter was actually made of tiny particles. Okay, so Democritus, sorry, got cut off there. So Democritus was a thinker, okay, which was like the best job that you could have in ancient Greece. Okay, being a thinker meant you just got to sit in the square or the Parthenon, and people would fan you with big palm branches and feed you grapes, and all you had to do was come up with cool ideas, right? Well, one of the days Democritus is sitting there, he decides, you know what, I think all matter is made of these tiny particles that you can't see. And everyone looked at the person who was supposed to be shading him with the palm branch and went, you let him be in the sun this long? Okay, he's talking about imaginary invisible particles. Okay, he's losing it. He's got sunstroke or something. Okay, because it didn't make sense. I'm supposed to believe something I can't see. Okay, meanwhile I know everything is made of 4 elements. Yeah, you're crazy. Okay, so his idea wasn't accepted for a few thousand years. Okay, in the end, he was proven right. Okay? But at the time, he wasn't. Okay? Other people like Plato and Aristotle, okay, they were more widely respected and they believed in the four-element model. Okay? Now, it wasn't all bad for Democritus. He left the sciences and went on to the arts instead. What did he come up with? Democracy. Yeah, that's named after Democritus. Came up with the idea of representative democracy. Okay, so it wasn't all bad for him. He just wasn't a science guy. But in the end, he was also right. So, okay. So if you know who Democritus is, yeah, I'd say that's kind of important. He did, after all, come up with the idea of the atom. He was never able to prove it, but it was his idea. Now, during the Middle Ages, a lot of stuff was discovered about the behavior of matter, okay? Properties of matter and behavior of matter. But it was done very secretively. It wasn't scientific work. It was trial and error work. And it was done by a group of people known as the alchemists. Okay? And the alchemists were trying to do things that we now understand to be impossible, okay? But of course at the time they didn't know that. Okay? They were trying to do things like turn lead into gold. Okay? It takes a cheap, readily available metal and turn it into something valuable. Okay? We now know, given our understanding of the structure of matter, that something like that would be impossible. Because lead is an element, and so is gold. You can't turn one element into another element. Okay? You would have to fundamentally change every single atom that material is made out of. There's no way to do that. Okay? They thought they could because they didn't understand what was happening at an atomic level. They saw that if they mixed things together, they would get a final product that was different from the two things they started with. Okay? So it was reasonable for them to think that they could do something of that nature because they just didn't understand, again, the atomic particle level of things that were going on. Okay? What they were doing was having chemical reactions. And those chemical reactions could produce different things. Okay? But they were still made of the things they started with. Okay? All right, so a typical alchemist's lab would have looked something like that. That's Da Vinci's lab. Okay? He was kind of an alchemist. He came up with lots of kind of strange ideas and flitted from one thing to another. Okay, so all you really need to know about the alchemists is that they did discover a lot of important things about matter, but they didn't communicate them. That was kind of the downfall, is there wasn't any communication. They were very secretive. I mean, if you're the first person who figures out how to turn lead into gold, that is not a secret you want to let out. Okay, and keep that to yourself and get filthy rich. Okay, so they didn't communicate these things between each other. True science, communication is key. Okay, so they hid a lot of things. Okay? It wasn't until these two guys came along that all sciences were sort of revolutionized. Okay? And again, I'm not worried about their names. It's Lavoisier and Bacon. Okay? You're not going to need to know those. But here's what they did. They invented the scientific method, which is the thing you use every time you do a lab. You have a problem, you have a hypothesis, okay? You make a procedure to test it, a controlled experiment, okay? You have results, you have analysis, and you have a conclusion. Okay? That's the scientific method. That's what they produced, and that's what turned alchemy, these secretive little people, okay, who were trial and erroring stuff, into a true science. And it turned all the sciences into true sciences because now there was this kind of set of steps to follow and rules about communicating your findings. Okay. All right, so the atomic theory or the particle theory goes like this, and you've probably heard this before. Okay, all materials are made of tiny, indivisible particles called atoms. Okay, that you've probably heard before. There's a few things though that you probably haven't heard before, okay? And that's what that means at a bigger level. Every element has different atoms. Okay, so if I have a big block of lead, okay, every single atom in that block is the same. All lead atoms are the same. That's why every piece of that block has the same properties. Okay? But if I have a block of lead, and then beside it I have a block of, I don't know, calcium, are they going to look different? Okay? Are they going to have a lot of differences? They are. And that's because lead atoms and calcium atoms are very different. Okay? They have different numbers of protons, they have different numbers of neutrons, different numbers of electrons. And it's the number of protons that determines the properties. Like calcium is a soft, kind of dull colored metal, okay, whereas lead, and it's quite light, okay, whereas lead is very, very heavy and shinier, okay, than calcium. So, sort of make sense there? Okay, that has to do with everything has its own particles and atoms are the heart of it. Okay, so this part here that's in bold, okay, I would say would be important. So an atom is the smallest particle of any element that retains the properties of that element. Okay? It's the smallest I can break something down to. Okay, so as an analogy, basically if I had this big block of lead and I could cut it into smaller and smaller and smaller pieces, okay, I could keep cutting that until I got down to a point where I couldn't cut it anymore. Okay, that level would be I have now single atoms. Now could I realistically cut lead that way? No. First off, lead's a metal, it's hard to cut. Okay, but secondly, even if I could, any cutting device we have is still going to be hundreds of atoms thick, if not thousands of atoms thick. That's not like, you're not going to have to worry about splitting the atom while chopping carrots at home, okay? Because your knife is thousands of atoms thick, even on the sharp edge, okay? They're incredibly small. All right, but if I could keep cutting it down, 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 I eventually have a whole bunch of single atoms, and every single one of them would have exactly the same properties, okay? Same number of protons, same number of electrons. Okay, questions on that part? Okay. All right, so let's talk about Dalton's atomic theory and then I'll give you a quick break here. So Dalton is one of the most important people in Science 10 chemistry. Okay, so Dalton is the person who came up with the atomic theory. Okay, he revived Democritus' idea about all materials being made of these tiny particles. Okay. He was a chemist and he had studied the behavior of matter, okay, and he understood, at least he thought he understood, okay, how it worked. Right? So I would say, let's get you to do this right now, copy down, if you are doing that, okay, copy down Dalton's 4 points, and then we'll talk about what each of them means here in a minute. Okay, so knowing these 4 points is pretty important. Like, if I was to say have a quiz this Friday, this would definitely be on there. Okay, so I would definitely know these 4 points. Okay. So the first point, obviously Dalton copied from Democritus. Hey, he had good material, so he kept that. What he had found was that made sense. Okay, the behavior that he had observed of matter and chemical reactions and things like that seem to fit with things being made of tiny particles, not being made of mixtures of 4 different things. Okay? It made more sense for everything to be made of small particles. Okay? The second point that Dalton came up with, okay, was that atoms of the same element were identical. Now, not all of Dalton's points have kind of held up over the years. We still consider them to be effectively true, but our modern sciences and technology have proven some of them to be not 100% true. Okay, so for number 1, for example, okay, all elements are composed of tiny, indivisible particles called atoms. They're not. Are they truly indivisible, or can we split atoms? We can totally split atoms. Okay, we have the technology, okay, we understand how that works, so we can split atoms. Is it something that you can do just on your own anytime you want? Thankfully, no. There's a lot of crazy out there. Okay, so thankfully, no, that's not something that anybody can just go and do. But we do know that some atoms, anyway, are divisible. Okay, atoms of the same element are identical. That is effectively true. It's not 100% true. It's effectively true. Okay, every carbon atom, for example, okay, will have 6 protons and 6 electrons. Most have 6 neutrons, but a very small percentage actually have more than that. Okay? They may have 8 neutrons. That's the stuff we call carbon-14. It's used in carbon dating. Okay? It's how they tell how old artifacts and things like that are. Okay? Carbon-14 is what we call an isotope of carbon. It still has all the same kind of chemical and physical properties of normal carbon, but it's slightly radioactive and breaks down. Okay? It still has 6 protons, so we consider it to be effectively identical to all the other carbon atoms. That sort of makes sense? Okay? It's still effectively true, so we still keep it in the theory. Okay, number 3. Okay? Atoms of different elements can combine with one another in simple whole number ratios to form compounds. So here Dalton says, here's how you make new things. You can put atoms together and that'll make something new. All right? But this part of it is very important. This goes back to the atoms are indivisible part of point 1. Okay? A chemical reaction is not going to split atoms. Okay? That's a physical process. So if, for example, I wanted to make water, I would take hydrogen gas, mix it with oxygen gas, and that would make water. Okay, I would have 4 hydrogen atoms on each side. That's why I put the big 2's in there. Okay, and I would have 2 oxygen atoms on each side. Okay. I haven't split any atoms. I don't have any fractions in here. Okay, does everyone kind of follow me? I wouldn't write this reaction like this. I wouldn't go can I have half an oxygen atom? No. Okay, that's what he means by the third point. Atoms can combine, but they have to be in whole numbers. You're not breaking an atom in half or into smaller parts because that's not allowed. Okay, atoms don't do that, so atoms always go together in whole number ratios, 1 to 1. So 1 atom of this, 1 atom of that. 2 to 1, 2 atoms of this, 1 atom of that. Water is an example. It has a ratio of 2 to 1. Okay, so they always combine in whole numbers. You're never going to have, well, like this. Okay, I would never write HO1 half. Okay, half an oxygen atom is beryllium. Okay, that's not what's going on here. Okay, everybody all right with the third point there? He's just saying when you put things together, you don't have fractions of an atom. All right, now the fourth point, okay, this fourth point is probably the most important, okay, because it was the nail in the coffin for alchemy. Remember, alchemists were trying to turn lead into gold, one element into another element, okay? That can't happen, and it was Dalton's experiments that kind of showed I can make new things, but they're always made up of the things I started with. I never make any new elements. I can make new compounds, I can make new materials, but they're always made of the things I started with, okay? So for example, this would be a chemical reaction. Except that I have to Okay, so in a chemical reaction, just so that we know the terms, okay, these are our reactants. They're the things that are reacting. Okay, and then on the other side, these would be called our, starts with P. Products. Okay, so this is what I start with, my reactants. This is what I finish with, my products. There are only 4 elements in this reaction. Did I make any new elements? No. I started out with lead, Pb, chlorine, Cl, sodium, Na, and oxygen, O. Okay? And that's all I have on the other side. Do I have new materials? I do, right? I made different compounds. I started out with lead-4 chloride and sodium oxide, and on this side, I have lead-4 oxide and sodium chloride. I have different compounds, but they're still made of the same things I started with. You cannot fundamentally change an atom in a chemical reaction. Okay? That's what the alchemists were trying to do. The alchemists were trying to do this. They're trying to go lead to gold. Okay? You can't do that. Those are 2 different atoms. I can't make a new element on the other side. I can make new compounds, but I can't make new elements. Everybody with me there? All right. I'm going to give you guys about a 5-minute break here, okay? And then we'll reconvene and talk about the different atomic theories, okay? Or models, I should say. All right, so I'll give you 5 minutes here just within the classroom, okay? All right, so Dalton did all this work, came up with the atomic theory, which was generally very well accepted. People thought, you know, well, this makes total sense. It agrees with all the experiments I've done, and what a great idea. Good job, Dalton. But there was a natural follow-up question to the atomic theory. Okay, hey, John, what do atoms look like? And he's like, didn't you read my point? They're really, really small. I don't know what they look like. I can't see them, and neither can you. People are naturally disappointed by an answer like that. Okay, so he has to come up with something. So he's like, okay, the sun is round, the moon is round, the earth's round, by the way. Okay, we got to set that point day 1. Okay, the earth is round. Okay. If you have a problem with that, that's too bad. The earth's round. Okay. So he said spheres are a commonly naturally occurring shape. So atoms are spheres. Okay, people are like, okay, can't see, I can't prove you wrong, let's go with that. Atoms are spheres. Now, does that account for protons, neutrons, and electrons? No, it's just a ball. Well, the ball doesn't account for the things we now know an atom is made up of. Of course, at the time, they didn't know about these things yet. Okay, so it was natural for them to assume, sure, an atom is a ball. Bigger things have, you know, a bigger sphere. So that's fine, we'll go with that, okay? Lead's bigger and heavier, so it's a bigger sphere than a carbon atom is. So that, okay, that's fine, that's what we'll go with, okay? But it didn't take very long before somebody was doing an experiment that showed the solid sphere doesn't explain my data, okay? So we start off with the solid sphere model, okay? It couldn't be broken down into smaller parts because nobody knew a smaller part existed, okay? And so that was fine. Persisted for, you know, a few years anyway. But a guy named J.J. Thomson was doing experiments in what we call electrochemistry. It's the chemistry of batteries. Okay? He was making cells, electric cells, okay, that would produce electricity. Well, a chemical reaction produces a current in a battery. But there was nothing to explain why charged particles would flow through a wire as a result of a chemical reaction. Okay? The wire wasn't getting bigger. Okay? You couldn't see the atoms move through the wire, so this didn't explain where the charged particles were coming from. So Thomson's like, there's a flaw in the model. Okay? Atoms may very well be a solid sphere, but there has to be more to them than that in order to explain why charges can move in a chemical reaction. So he modified the existing model. He said, I'll keep the solid sphere, but I'm going to say that embedded very loosely on its surface are small negatively charged particles called the electrons. Okay, because they make electricity, so there's a logical name for them to get. Okay, this became the plum pudding model. Okay, so I would say probably no plum pudding model. Okay, it was a revision of the existing model, and it explained how electrons could flow as a result of a chemical reaction. Okay, what we're seeing here is an example of how science is supposed to work. We have a model, we have an idea, and then something comes along that disproves it. So we have to come up with something new. Okay? This happens many times throughout the history of chemistry. Now, there are some flaws with the plum pudding model as well. Okay? We already at this point knew that all matter, or all elements, were electrically neutral. That means yes, there are these negatively charged particles called electrons, but an atom is overall got a charge of 0, which means there's got to be some positive charge hanging around somewhere to offset all these negative charges. So Thomson explained that by saying the big central part, sphere, is positively charged. And then these negative charges are stuck to it because opposites attract. Well, okay, that made sense. Okay, people were okay with that. Okay. Thomson's model also didn't last. Okay, because it wasn't very long after that where physics started to get involved. Okay, and we started proving that there were actually lots of things inside an atom. Okay, the idea that a whole big mass could be positively charged didn't explain things very well, so we went to having small positive charges, bigger than the electrons. Okay, but they're positively charged. They're protons. Okay, now coming up with that didn't explain where all the mass of an atom comes from. So there had to be some other particles in there that didn't carry a charge that would help make up all the extra mass that we knew matter possessed. Those would be the neutrons. Okay, so a lot of experimentation went on, okay, during this couple of hundred years worth of time to kind of arrive at there's got to be other parts to this. Okay, people were accepting of most of the models. But then there became a division. Okay? And the division came between people who thought there should be free-floating or freely moving electrons and a central dense nucleus, and people that liked the big particle with everything stuck together. All right? So somebody had to come along to kind of prove it one way or the other. Okay. So lots of different ideas here. This is kind of the schism, right? The breaking up, or the two groups of thought. Okay? You got this big mass, and there's protons and neutrons, or there's a central nucleus with protons and neutrons and electrons orbiting it. Okay? That was kind of where there was a divergence. Okay? Chadwick discovered protons were not the only one. Okay? Chadwick is the person generally credited with discovering neutrons or calculating that they should exist based on mass. Okay? So you can just write Chadwick neutrons. That'll be good. But probably the most important scientist and experiment is Rutherford. Okay? Rutherford is the person who's credited with discovering or proving the existence of the nucleus and coming up with the nuclear model of the atom, which we generally accept today. Okay? So, Ernest Rutherford, okay, felt atoms could not have all these particles floating around randomly. Plum pudding and solid sphere models were not accurately explaining experiments. Okay, so he conducted an experiment where he took a sheet of gold foil. Okay, so you guys have all used tin foil before, right? Okay, tin foil's like thousands of atoms thick. Okay, it's still, even though it looks really thin, atoms are really small. Okay, what Rutherford did is he got a sheet of gold foil. Right? But it was super thin. So where tin foil, you can go like this. The gold foil would have been more like a Kleenex. Okay, like it would have been really, really, really thin, only a few atoms thick. Okay, and what he did is he set that up in front of what was effectively an X-ray machine. Okay, now if you get an X-ray, okay, it shows your bones, right? Why? Well, because the X-rays come in and they go through all of your soft tissue. Okay, they'll go through your organs and they'll go right past. Okay, but they'll hit the denser parts of you, your bones, and they'll reflect off. Okay, and so when you get an X-ray and you see the picture, what you see are the parts of the body that reflected the X-rays back. Okay, what Rutherford did is he said, I've got this sheet of foil, and it's only a few atoms thick, and I'm going to shoot X-rays at it. And if atoms are really big, all of the X-rays will reflect back. If atoms are really small, then the X-rays will go, some of the X-rays will go in between, and they'll get through this sheet of foil. Okay? Now, most people are like, that's crazy talk, but okay, go for it. Right? So what he did, okay, is he set up an experiment that looked something like this. All right, so you gotta remember, this is a long time ago. So he had photographic film, right? You guys are aware that cameras used to have this stuff called film in them, right? Okay, I know you guys have probably never used one, but so they used to have this stuff called film, and if you exposed it to light, it would change color and form an image. Okay, he just surrounded this gold foil, okay, with photographic film, and then turned on the X-ray machine. Now, he expected that the nucleus would be very, very small, and that he was just going to get a bright spot behind, because pretty much everything was going to get through. All right. But what actually happened was he, yes, got a bright spot behind, but not nearly as big as he had hypothesized. He also got bright spots in a whole bunch of other places, okay? Implying that some of the X-rays hit the atoms like at an angle, so like obliquely, and got deflected, right? So something like this. So lots of the X-rays just went right in between, because his experiment proved that an atom is actually a lot of empty space. Okay? So the nucleus would be the only dense part. So some of the X-rays went right through. Some would hit a nucleus and get deflected. Right? Those would be the ones that would make a bright spot over, at an angle instead of right behind. Okay? So from this experiment, and based on how many of the electrons actually, or the X-rays actually got through and how many were deflected, he was actually able to get a pretty reasonable size calculation for the nucleus of an atom. Okay? And that gave us a better idea of how big protons and neutrons actually were. Okay? So here's the big thing you need to know, or you need to have written down somewhere. First off, Rutherford. Okay? Rutherford gold foil experiment. Okay? Probably the most important experiment in chemistry/physics. Okay? And that gold foil experiment proved the existence of the nucleus. Okay, so Rutherford does this experiment, proves the existence of the nucleus, and then they ask him, all right, make your model. We want to know what you think the atom looks like. Okay? And this is where Rutherford messed up. Okay? Rutherford was working kind of with a guy named Bohr, and they had a disagreement at this point on what the electrons look like. They were fine with, hey, we proved the nucleus. That's where the protons and neutrons are. They're bigger. Okay? They stick together. They're in the middle. Okay? This is Rutherford's model right here. Okay? So you got a central dense nucleus, and then all of the electrons orbiting the nucleus. But Rutherford's model had them all orbiting at the same distance. And then their orbits were just kind of offset by a few degrees. That is okay, but not great for small elements. It's terrible when you're talking about an element that has over 100 electrons. The separation angle between all of those electrons starts to get really small. And electrons are all negative, so what do they do to each other? Like things, they repel. Okay? So trying to put all these electrons the same distance from the nucleus doesn't really work from a repulsion kind of point of view. Okay? So he came up with this model of the atom, which was basically abruptly rejected. Okay? His partner, Bohr, came up with this idea that it was like the planets around the sun. The nucleus was the sun, and electrons orbited at different distances from the nucleus. And there was some evidence to support that some electrons moved faster and had more energy and stuff like that. So his model was generally accepted for quite a while. In fact, we still sometimes draw them with the Bohr model. But we discovered shortly after that that electrons actually behave much different than that. Okay, so even though it seems like, hey, we've got the nucleus, everything should be hunky-dory, there was actually a whole bunch of arguing then about, well, what do the electrons do? Nobody's ever happy. Okay, so there was a lot of argument about what are electrons doing. Okay, so I would say definitely no Rutherford, gold foil, prove the nucleus. Okay, Bohr, planetary model, yeah, you can know that a little bit, it's less important. Okay, but the next most important person is de Broglie. He's the one whose model we accept now. Okay. Okay, so this is what Bohr thought, right? He had the planetary model. Electrons were different distances from the nucleus, okay? And it works to an extent. Okay. De Broglie proved what we currently accept. Okay. How many people have ever seen that glow-in-the-dark stuff? You put it out in the light, and then if you take it into the dark, it glows for a short period of time. Okay, so it was actually materials like that, okay, that explained de Broglie's model. Electrons, when they gain energy, can be excited. Okay, and when they get excited, they move faster. Well, if you're trying to orbit the nucleus at a certain distance and you get moving really, really fast, you can't stay that close. Okay? It's like trying to turn a corner too sharp. You kind of skid out because you're going too fast for a corner of that radius. Okay? So they actually jump. If they get a lot of energy, they'll make what we call a quantum leap from one orbital to another, okay, to a higher energy orbital. So for those glow-in-the-dark materials, that's what's happening when you have them out in the sun. The electrons are gaining energy and they're making quantum leaps, jumping to higher energy positions. When you bring them into the dark, there's nothing to hold them there. They rapidly lose that energy and they fall. And when they fall, they give that energy off as light. They glow in the dark for a short period of time. Okay? So de Broglie was using this to kind of explain, here's how electrons behave. Every atom has a different sort of set of, or configuration of electrons. Okay? They're likely to be here, they're likely to be here, they're far less likely to be here. Okay? And that's basically explains this idea of the quantum leap. Now, another thing that's crucially important for all life on Earth uses this same idea. Photosynthesis. Okay? When light hits the leaves of a plant and hits the chlorophyll molecule, the electrons in the chlorophyll get excited and they jump to higher energy levels. And when they fall back down, that's the energy that's used to make sugar. Okay? That energy is used to break up carbon dioxide and water and reassemble them as glucose. Okay? So it's the same idea. It's electrons gain energy, and then they give it back when they fall back down. Okay? Does that sort of make sense? All right, so that's de Broglie's model. Okay, so de Broglie surmised that electrons could not be found in fixed positions, but that they moved around based on their energy. And so he came up with what we typically call the electron cloud model. Okay, so the electron cloud model says electrons can be found in this area. There are areas within the cloud where they're more likely to be found, and there's areas of the cloud where they're less likely to be found. But electrons generally surround the nucleus in a cloud, and their positions can change. Okay, the Bohr model did not account for that. The Bohr model said they're in this orbit, you'll always find them here, which isn't true. All right, so here's basically what I'm gonna ask you to do on, let's say, a quiz or an exam. Okay, I'm gonna ask you to draw a picture of an atom. Which model should you draw? You should draw this one. Okay, you should draw the electron cloud. Now, within that question, I would also want you to be able to tell me how many protons are there, how many neutrons are there, and how many electrons are there, okay, in this one. So let's say I asked you to do this for an atom of beryllium, okay? So on the periodic table, okay, beryllium's square, okay, looks like this. You got the atomic number up in the top left. You have the atomic mass in the top right, okay? And then you've got the electronegativity, which is not important, okay? So we've got this as the box for beryllium. How many protons does a beryllium atom have?
4.
4. Okay, the atomic number, the number in the top left, tells us the number of protons. Since atoms are electrically neutral or have no net charge, how many electrons must there be? 4, right? If I've got 4 protons, that's 4 positive charges. If I'm going to have an overall charge of 0, then I also have to have that many electrons. How do I figure out how many neutrons there are? Anybody remember from Science 9? Have to do a little tiny bit of math. Okay, to get the number of neutrons, okay, okay, is the atomic mass minus the atomic number. Okay, this is the atomic mass, 9.01. Okay, so how many neutrons in a beryllium atom? What's 9 minus 4? 5. Okay, because we don't have 0.01. Can you have 0.01 neutrons? No, you just round it. Okay, it'll always be obvious. You're either going to round it up or you're very clearly going to round it down. Okay, in this case, 9.01 minus 4 tells us that the number of neutrons is 5. Okay, so if I'm drawing an atom of beryllium, this is what I would do. Okay, I would draw Okay, 5 neutrons. 4 protons, and then 4 electrons in the cloud. I would probably put a legend beside it just for clarity, right? I would probably go. Spoiler alert, I will ask that on your unit exam. And it'll be a 5-mark question.
What is the 5 there for?
Oh, that's the number of neutrons, sorry. Okay, so it would be a 5-mark question on a unit exam, probably a 5-mark question on a quiz as well. Okay, here's what you'd get the marks for. 1 mark for the right number of protons, 1 mark for the right number of neutrons, number of electrons. Okay, the correct model for 1 mark, putting everything in the right place in that model for the 5th mark. Okay, is that 5 easy marks? It's pretty straightforward, right? Okay, so by the way, guys, I do this all the time where I tell you exactly how I'm going to ask this. If I do that, you should totally write it down because I'm not lying to you. Okay, if I tell you I am going to ask this, I mean it. Okay, it's a great way to, later when you're studying, go, oh, Coder, I wrote down that Coder said he was going to do this. I know exactly how to prepare. Okay, all right, we will leave it there for today, guys. Good work. Tomorrow we're going to answer some questions to do with this stuff and then move on to naming. Okay. If you can, having the workbook for sure printed for just this unit for tomorrow would be great. Notes package, also good, but workbook, great. Okay, for tomorrow.